We're going to work some problems here to review for the test on work fluid force, moments, centers of mass, and also area and volume. So this is part one. We'll talk about the area and volume part on the second part. So first, a couple of work problems. A ship is anchored in 50 feet of water. Its anchor weighs 2,500 pounds and the chain weighs 10 pounds per foot. So we're going to ignore the buoyancy and the water resistance and all that. So we're just going to focus on just as if this was in an idealized situation. So first, the work done in raising the anchor alone from the bottom of the ocean to the surface. So here our force is going to be constant. So we have work is going to be force times distance. And the force is the weight of that anchor, which is 2,500 pounds. And the distance is we're going to bring it up 50 feet from the bottom of the ocean to the surface. So 5 times 25, 5 quarters is 125, and we're going to have 3 zeros. So that's going to be 125,000, and it's a weird unit, but that's going to be in foot-pounds. So that's the amount of work done just in bringing up the anchor itself. Now the chain is going to take a little bit more figuring here. So when this chain is all the way extended, we're going to have 50 feet of that chain, and that's going to weigh 10 pounds per foot. So that whole length of chain is going to be 500 pounds rather. So I'm going to think of us as maybe putting in, I'm trying to think what color to put. I'm going to imagine we're going to put kind of an axis in here, and I'm going to think of 0 as being here and 50 as being at the top. So when we're at 0, the weight of that chain is going to be 50. If I imagine bringing it up to, say, up 10 feet, then it would be, the weight would then be 10 pounds times that 10 feet less. So each time I bring it up a foot, I'm going to lose 10 pounds of weight, which is like our force. So our force is going to be variable. As we pull up that chain, the weight or the force is going to decrease by 10 pounds per foot. So this is going to be like our force or our weight. So we're going to imagine then our delta work is going to be, we're going to take that force times a little bit of distance. And then we'll recalibrate our force because it would have changed by then. So that means our delta work is going to be this 500 minus the 10y. That's going to be that length of the chain times 10 pounds per foot, and then that's going to be times that delta y. We're going to add all that up, and it's going to become an integral, and so our work is going to become an integral. We're going to go from 0, which is putting us on the bottom, up to 50, which will put us up at the top. And you can kind of see that when we get to y equals 50, we'll have 500 minus 10 times 50 is 500 minus 500. So there'll be no more chain left, and so the weight or force will be 0. So we are going to actually have to integrate 500 minus 10y dy. So that's, the integral is the easy part. So integral of y is 1/2 y squared, so that'll be 5y squared. We're going from 0 to 50. So we're going to get 500 times 50 minus 5 times 50 squared, and then plugging in 0 is just going to be 0. Well, let's see, we're going to get, I'm going to think of that as factoring out one of those 50s, and that will leave us with 500 minus 5 times the other 50 is 250. So that's going to be 50 times 250. 5 times 25, 5 quarters is $1.25. So that's going to be 125 with 2 zeros. So that's going to be 12,500 foot-pounds. So that's going to be how much work it's going to take to lift the chain up, and I didn't ask, but I'll ask that right now. So what's the total work done in lifting that chain and anchor from the bottom of the ocean up to the surface? And that's going to be our 125,000 foot-pounds plus another 12,500. So I guess that will be, what, 137,500 foot-pounds of work? Okay, let's look at pumping water out of a tank. So we have a conical tank that has a radius of 10 feet and a height of 20 feet. It's filled with water and water weighs 62.4 pounds per cubic foot. A pump takes the water to a point 5 feet above the top of the tank. What's the work done in emptying the tank? So how it gets there, you don't have to really worry about. So from what I've looked at work, you can imagine just doing it the most efficient way, and that's the same. So we're going to imagine taking a slice of water here, a slice of water, and moving that from where it is up to this place 5 feet above the tank. So we're going to get our work is going to be this force times distance. Force we're thinking of as being that weight. So if we want to look at that little slice of water there that we have, we're going to try to figure out what is its weight, and then we'll try to figure out how far we're going to move it. So this is our delta force, is going to be the weight of that water. So that's going to be our delta volume times our weight density of the water. That's going to be our weight of that water, which we're going to call our force. So the delta volume is going to be a little cylindrical slice there. So we need to know a radius and a height. So the height we can see is going to be this little delta. That's going to be our delta, I guess we can call it delta y perhaps. So if we imagine now we're going to put an XY axis on here, and I'm going to think of this coming right from the bottom up to the top. I'm going to think of this as being 0. The top of the tank is going to be 20, and the level that we're bringing the water to is going to be 25. So we need the radius of our slice of water there. Because our height is a delta y, we need this radius in terms of y. So this has to be something in terms of y. So that means we need to look at an equation of a line going along the side of the tank there. We're going to think of this point as being the origin. And since we're rising 20, the height of the tank, and running 10, that's the radius, that looks like our slope is going to be 20 over 10, or 2. So that line is going to be y equals 2x. So at whatever height we're at here, that radius that we're looking at here is going to be, let's see, we want that to be, we're going to write that as x equals 1/2 y, because we need that in terms of y. So whatever our height is right here, that radius is going to be 1/2 times that y value. So that is going to make our delta force be pi times 1/2 y squared. There's our delta y, and our weight density we said was 62.4 feet per cubic foot, or pounds per cubic foot. So you can see that if we have a foot measurement here with y, that's getting squared times another delta y. We're going to have, this is our delta volume right here, which is going to be in cubic feet. That's going to cancel with our pounds per cubic foot and give us a force that's going to be in pounds. So let's see. Can we clean that up a little bit maybe? So we can say that the 1/2 squared is 1/4. So we're going to get 62.4 pi over 4 times y squared times our delta y. So that's our delta force. Now we have to figure out our delta work, which means we're going to take that force and we got to figure out the distance we're going to move that. So if we look at our slice of water right here, so that's sitting there at whatever that y value is. So our y is going to be counted from the bottom up. So if this was maybe 5, say, so we are looking at a slice right in here where that y value is 5, we would have to move that slice all the way up to there. So it would be 25 minus that y value of 5 would be the distance that we would have to move that. So that's going to be our force, or maybe I should say our delta force, and we're going to have to multiply that. We're going to have to move that a distance of 25 minus y to get it all the way up 5 feet above the top of the tank. Okay, so then we're going to get, that's going to look like, I guess we've got our 62.4 pi over 4 times y squared, and now times a 25 minus y. And we've got our delta y in there from our delta force. So that's our delta work. So the total amount of work we do, and let me pull that constant out, the 62.4 pi over 4. It's going to be an integral. So we're going to count our slices. Remember, we're going to count our slices through here just until we go from 0 on the bottom up till we get to the top of the tank, which is 20. So we're going to go from 0 to 20, and if I distribute that, that'll be a 25y squared minus y cubed dy. I'm just not feeling doing all that, so I'm going to pause the video here for a moment, and I'm going to put all this into my calculator and use numerical integration, and we'll see if we get the same result. So I'm getting 1,306,902.544, and that's going to be in foot-pounds. Sounds like a lot of work to me. Okay, let's see what else we got here. Okay, we're going to do a little fluid force here. So we have a dam that has a gate on it shown at the left. So our gate is this triangular metal shape here. It's got 6 feet across the top, which is right at the water level, and then it's got a height of 4 feet there. And we want to know what is the fluid force exerted on the gate. And we know the water is 62.4 pounds per cubic foot. So we know that our pressure is going to be the weight density, that's the weight density of the water, times the depth. So I think I'll just call that D for depth right now. So and then we're going, so for that, we're going to have our 62.4. Now the depth, we're going to have to put in here again an XY axis. So I'm going to put the y-axis coming up there, and you can do it different ways. Some people like to put the origin up at the top. I'm going to put the origin here because in a moment here we're also going to need to get this side here, and I like to have the origin here. It just makes that equation of that line easier. So the equation of that line is going to be, we're going to rise 4 and run 3. So that's going to be y equals 4/3 x. So that means that our depth this is going to be 4 feet up to here. This we're calling 0. So if we are at a y value of 0, our depth is 4. So that's going to make this be 4 minus y. And when we're at a y value of 4, our depth is going to be 0. So that's going to be that's the fluid pressure. So that's going to be, since we're multiplying by this right here, is going to be a foot measurement times our pounds per cubic foot is going to give us pounds per square foot. So then we are going to look at a slice of that water. So we are going to take a slice that's all at the same depth, because then the pressure along here is going to be the same everywhere. So on this slice right here, the pressure is, since it's at the same depth, it's going to be that same thing. So that means that our delta force is going to be our pressure, our pounds per square foot, times our little area of that rectangular slice. And that rectangular slice is going to be base times a height. So you can see that the height of that is going to be a delta y. That means we want to get the base in terms of y. So let's see what we can do with that. So we've got our pressure times, we're going to have our height is going to be that delta y. And now we're going to see that this base, that this part right here is x, the x coordinate of that point, and because of the symmetry, the base is going to be 2x. But we want that in terms of y because of our delta y, so that means in our equation y equals 4/3 x, we're going to say that's x equals 3/4 y. And so that is going to make we're going to have our pressure, that's our pounds per square inch. We've got our delta y, and then we're going to get 2 times that 3/4 y. And that's going to be our delta force. So our delta force, let's see, we've got, should we bring in the 62.4? We've got the 4 minus y. That is our pounds per square inch. That's our pressure. And then we've got our delta y, and that looks like a 3/2 y. So with a little cleanup here, let's see, I'm going to take the 3/2. So 1.5 times the 62.4 is going to be a 93.6 times, and I'm going to go ahead and distribute that y through there. So that's going to be 4y minus y squared and delta y. So there's our force, our delta force. So that's how much fluid force is being applied to a rectangular slice. Now we want to add those slices up. We want to add those slices up as we imagine these kind of rectangular slices here, going from 0 up to a height of 4 there. So that means our force is going to be, I'm going to pull that 93.6 out. It's going to look like an integral going from 0 to 4 of 4y minus y squared dy. So once again, I'm just not feeling doing any more work, so I'm going to pause it and throw that on my calculator. And I'm getting 998.4. And that's a force, so that's going to be a measurement in pounds. That's the force that's acting on that triangle, that triangular gate. All right, well, that was a warm-up. Now it gets a little harder because we changed the geometry of it from that triangle to now a semicircle. So now it's submerged in the water, and again we have water is 62.4 pounds per cubic foot. And now, since that's a semicircle, I'm going to put in an XY axis here again. So I'm going to imagine now I'm going to put the origin here on the surface right in the middle of our semicircle. So we want to think of the equation of that semicircle. So a circle centered at the origin, radius 3, would be x squared plus y squared equals 9. Now we are going to be looking at a slice that's going to come along here, kind of like we did on the last one. And so we're going to get our pressure, we'll get that in a moment, and our delta force, remember, is going to be our pressure, and then that's going to be times our delta area. So we're going to need a delta area here. And so that area, that delta area, is going to be the base times the height of that rectangle. And we can see that the height of that rectangle is going to be a delta y. So that's this part right there is a delta y, and that's what drives us. So that means we've got to get our base in terms of y. So we can see that this rectangle, that the x-coordinate of this point right here is half of our base. So our delta area is really going to be 2x times that delta y. But we have to get now the x in terms of y. So that means we're going to subtract that y squared to the other side. We're going to take the square root of that. Now we would be taking positive and negative square root of that, but our x value here is always going to be positive. So we can just ignore that negative part and get that the x is going to be the square root of 9 minus y squared. So that's going to make our delta area be 2 times that. So that's going to be 2 times the square root of 9 minus y squared delta y. Now our pressure is going to again be the weight density times the depth. And the weight density is that 62.4, that's the pounds per cubic foot. And the depth, let's see, if this is 0, our depth is going to be, the y-coordinate here is going to be a negative number. So the depth is going to be a negative y. Does that make sense? So our delta force is going to be our pressure. That's going to be that, I'm going to take the negative out, negative 62.4 times y, that's our force, times, then we've got our delta area, which is 2 square root of 9 minus y squared delta y. Okay, I'm going to bring that 2 out there. So it looks like our delta force is going to be a negative 124.8. And that's going to look like a y times the square root of 9 minus y squared delta y. Okay, now the, actually that's, that's right. So our force then, we're going to integrate this. I'm going to pull out the negative 124.8, this integral. Now here's where we got to think where we're going from. So we're integrating with respect to y. So we're going to go from here to here. That's going from negative 4 to 0. And because our origin, remember, is up here at the surface of the water. And our integral has become one that may look messy, but we can actually do this. And then that's going to become a dy. Well, let's see what we can do. Negative 124.8. Now, we need a little u substitution here, I think. So we can say that u, whoops, not a very good u is going to be 9 minus y squared. So du is going to be a negative 2y dy. So dy will be du over negative 2y. So that's going to become an integral of, we'll get the y, this is going to be the square root of u, and our du is going to account for that other y. So, need my color scheme here. So we're going to cancel those y's. So it looks like that negative is going to come out, the negative 1/2 is going to come out. So we're going to be back to a 62.4, I think. And we've got the integral of u to the 1/2 du. Should we change our u limits? What the heck? So if we have u of negative 4, that's going to be 9 minus 16. Oof, I don't know if I want to do that or not. 9 minus 16 is a negative 7. I think I'll leave the u limits for now. Let me see if this works out with the right sign. So I'm going to ignore the limits. Let's get 62.4. That's going to be u to the 3/2, and then we're going to get 2/3 here. And we're going to, I'm not ready yet, so that's going to be, we're back to 124.8 over 3, and times, we're going to call that 9 minus y squared, going from negative 4 to 0. Is that right? Oh, goodness. We're not going from negative 4, we're going from negative 3. No wonder the numbers were not looking good. Okay, hold the phone there. That should have been negative 3, not a negative 4. Sorry about that, but that's good news in the end, I think. So we're not going to try to, these would have come out very nice. So if we're going to go from negative 3 to 0, this will work out well. So we plug in 0, relatively speaking. We get 9 minus 0 is 9, square root of 9 is 3. That's going to cancel with that 3. So I think we're going to get 124.8. When we plug in the negative 3, that's going to all be 0. So that's going to be just minus 0. And so we're going to get that total force is 124.8 pounds. Boy, that worked out pretty slick in the end. I just got the right limits from the beginning. Okay, let's do a center of mass problem. We need to impose an XY axis here. So I'm going to put it here. So I'm going to call the origin that lower left-hand corner. I'm going to try to divide this into rectangles. We're going to find the mass of each of those rectangles, which will be just its area, and then we'll try to find its coordinates. So I'm going to call this 1, 2, 3, 4. So mass 1 is going to be its area, and that looks like it's 2 by 4, so that's going to be 8. It's going to be centered at, the x-coordinate is going to be at 1, and the y-coordinate is going to be at 2. Our second mass is going to be, since that's 1 by 2, that's going to be a mass of 2. It's going to be located at the middle there. So that's going to be, this distance is 2, and so that's going to be 2.5. So its x-coordinate is going to be 2.5. And this, since this is 4, and this much is 2, that means we're going to be up 1. So it's going to have a location, a center of mass at 2.5, comma 1. Mass 3 looks like it's going to be, let's see, we got 2, 3, this is 2 across, so that's going to be 2 times 3 is 6. I think its mass is going to be 6. It's going to be centered right in here, which is going to be, let's see, that's 2 plus 1 is 3. Another one makes that an x value of 4. And since that's going to have a height of, it looks like 3, I think, so that's going to be 1.5 for the height, and mass 4. Let's see, that's going to be, we have 2, what do we have? 2, 1. So I think this is going to be a 1 by, and we have 2, 3, 4, 5. So this is 2 across there. So I think its mass is going to be 2. And that's going to be 2, 3, 4, 5. So that's going to be at 6 and 1/2, I think, is its height. Okay, so we want the moment about the y-axis. So that is going to be the masses times their x distance. So that's going to be 8 times the x distance is 1 plus 2 times 2.5 plus 6 times 4 plus 2 times 6. So I think that's going to be 8 plus 5 plus 24 plus 12. So let's see, it's 36, 41, 49, I believe, is that moment about the y. The moment about the x is going to be the masses times their y distance, the distance from the x-axis. So that's going to be 8 times 2 plus 2 times 1 plus 6 times 1.5 plus 2 times 0.5. So that's going to be 16 plus 2 plus, what is that, 9, I think, plus 1. So that's going to be 10, 28. And the sum of the masses is going to be 8 plus 2 plus 6 plus 2. So that's going to be 10, 18. So the x-bar, the x-coordinate of the center of mass, is going to be the moment about the y divided by the sum of the masses. And so that's going to be 49 over 18. And I think that's about all we can do with that. And y-bar is, the y-coordinate is going to be the moment about the x over the sum of the masses. I think that's 28 over 18. I guess we can call that 14/9. And so that is going to be our center of mass. Not very pretty, but 49/18, comma, 14/9. Okay, now we'll do one where we got to do a little calculus. Okay, so now we're going to find the centroid of the region of a planar lamina with density rho and bounded by the curve y equals 9 minus x squared and y equals 3 minus x. So I think we're going to need our points of intersection here. So if we take 9 minus x squared, set that equal to 3 minus x and solve. I'm going to bring it to the right side. That lets me make the x squared positive. Got a minus x, and that'll be a minus 6. So far this is looking good because that factors nicely into x minus 3, x plus 2. So it looks like our points of intersection are going to be at -2 and at +3. Okay, let's take a little region here. So we are going to imagine looking at this representative rectangle. So we need the moment about the y-axis, and that's going to be its distance from the y-axis, which is going to be x, times its mass, which is going to be the area. So let's see, our delta area is going to be our base times height. That's going to be our top curve. That's going to be our 9 minus x squared minus the bottom curve 3 minus x, and then times a delta x. So that's going to be a 9 minus x squared minus 3 plus x. So I think that's going to be 6 plus x minus x squared times a delta x. So our delta mass is going to be just our rho times our delta area. So it's just going to be a rho times that. Okay, so we are going to take, let's see, the distance to there. So, and we're going to imagine that's all placed right there. So the mass of that entire rectangle there, which is given by that delta area times the rho, the density, is going to be sitting at that point right in the middle. Its distance from the y-axis is going to be x, and then we're going to take it times that. I'm just going to write it right now as the delta mass. So that's going to be x times, it looks like 6 plus x minus x squared delta x, and maybe I'll squeeze in a rho there. And we're going to have to sum all of that up. So the moment about the y is going to be our rho times, and it's going to become an integral going from -2 to 1 of 6 plus x minus x squared, and that's going to become a dx. I'm going to come back and get these on my calculator in a moment. Let's see if we can find our moment about the x-axis. This is the hard one, because now we're going to have that little delta mass. So we're going to have our rho times, and this was our top curve minus the bottom curve. That's 6 plus x minus x squared. And we have our delta x. Now times its distance from the x-axis, and this point right here, its distance from the x-axis is going to be the average of our top curve and bottom curve. So that is going to be our 9 minus x squared plus the 3 minus x divided by 2. So that's our distance. Oh goodness. So let's see. We can bring that 2 out with the rho. We've got our 6 plus x minus x squared. I'm going to do some minor cleanup here. I think we can make that a 12 minus x squared. And we've got our delta x. I'm not going to worry about multiplying that out because I'm going to put it on my calculator in a moment anyway. Haha, did you catch that? In a moment. So that's going to be rho over 2. That's going to be that integral from -2 to 3 of 6 plus x minus x squared times 12 minus x squared dx. We need our mass, so the sum of our masses is going to be that rho times that integral from -2 to 3 of our area. So in our delta area was that 6 plus x minus x squared dx. So we are going to get these in a moment on our calculator, and then we're going to try to get that x bar is going to be the moment, the y moment, the moment about the y-axis over the sum of the masses, and the y bar is going to be the moment about the x over the sum of the masses. Okay, I'm going to pause a moment and see if I can get some numbers in here. Okay, so as I did that, I noticed that I left off the x that I needed from that moment about the y. So I fixed that, and that gave me, at least what I got for a moment about the y was a negative 2.25, and the moment about the x I got to be 78.3, and the sum of the masses to be 13.5. So that led to an x bar that's either as a decimal negative 0.167 or that's a fraction negative 1/6, and the y coordinate of the center of mass I got to be 5.8. All right, I think that's all I got for here. Very good.